When we look up, the night sky seems endless, yet each point hides a scale that dwarfs our daily measures. A single glance can stretch from a backyard to the edge of known space. The numbers involved are hard to swallow, but they shape every story we tell about the stars. Let's start by putting those numbers into plain sight. The Sun's diameter measures about 1.4 million kilometers, while Earth spans just 12,700 kilometers across. That makes the Sun roughly 110 times wider than our whole planet. If we placed Earth at the Sun's surface, it would look like a tiny pebble pressed against a hot skillet. I find it hard to picture the sheer size difference without a reference. Imagine a basketball representing the Sun. The Earth would be a grain of sand rolled onto the same surface. The contrast is stark, and it reminds us how small our world truly is in its own system. The Moon sits 384,000 kilometers away, a distance light covers in about 1.3 seconds. In terms of minutes of light, that is roughly 0.02 minutes, hardly a whisper of time. Yet that brief flicker of photons travels across a void that feels immense to us. When we think of minutes, we usually count heartbeats, not the stretch between two bodies. The Moon's light travel time is a reminder that distance can be expressed in the same units we use for fleeting moments. It makes the abstract feel a little more tangible. A light year is the distance light travels in one Earth year, about 9.46 trillion kilometers. To ground that, picture driving non-stop at 100 kilometers per hour for a whole year. You would cover barely 1/10 of a light year. The gap between everyday motion and this astronomical unit is enormous. Even a marathon, 42 kilometers, is a minuscule fraction of what a photon covers in a single second. If we stretched a piece of string from here to the nearest star, Proxima Centauri, the string would need to be 4.2 light-years long, far beyond any human-made rope. Our solar system, with all planets out to Neptune, spans about 0.001 light-years, a speck inside the Milky Way's disk. The Milky Way's diameter is estimated at 100,000 light-years, a scale that dwarfs the entire planetary neighborhood. In other words, the Sun sits in a tiny neighborhood within a vast galactic suburb. If we place the solar system at the center of a map, the nearest star would lie on the edge of a single grain of sand. The Milky Way itself would be a grain of sand on a tabletop, and the tabletop would be a speck in a much larger arena. The layers of scale keep folding into each other. The observable universe stretches about 93 billion light-years across, a sphere that includes every galaxy we can, in principle, see. That number is hard to hold in mind. It is larger than the distance light could travel since the universe began, because space itself has expanded. We often hear, "the universe is huge," but the phrase hides a precise measurement that guides every calculation we make. The 93 billion light-year figure sets a hard boundary for what our telescopes can ever hope to capture. Anything beyond remains forever hidden from direct view. Why does perspective matter when we tell stories about the stars? Because the numbers we choose shape the picture we paint. A description that focuses on kilometers can make a nebula feel close, while using light years pushes it far beyond immediate grasp. The scale we adopt determines the emotional distance we feel. If we describe a galaxy as 1,000,000 light-years across, the mind may slip into abstraction. Yet saying it would take a beam of light 1,000,000 years to cross it ties the size to a familiar process. The shift from abstract to experiential changes how we relate to the object. We don't really know how many more layers of size await discovery beyond the observable edge. Theories suggest an infinite expanse, but without data, the idea remains speculative. Acknowledging that uncertainty keeps us honest about the limits of our measurements. The Sun's mass, about 330,000 times Earth's, adds another dimension to the scale discussion. Mass and size often travel together, but not always. A neutron star can pack more mass than the Sun into a sphere the size of a city. This contrast shows that size alone does not tell the whole story. When we convert distances into travel times, the numbers become more human. Light takes 8 minutes to reach Earth from the Sun, a brief pause in a day's rhythm. That same light would need 2.5 million years to cross the Milky Way, a span that dwarfs a human lifetime many times over. The Milky Way's spiral arms stretch outward, each arm spanning tens of thousands of light years. If we walked along an arm at a steady pace of 1 kilometer per second, it would take over 10 trillion years to reach the end. The exercise highlights how our ordinary pace is meaningless on galactic scales. Even the nearest galaxy, Andromeda, lies about 2.5 million light-years away. Its light left the galaxy when early humans were still carving stone tools. The fact that we can see it at all is a triumph of physics, not of proximity. It reminds us that near and far are relative concepts. Our instruments, from radio dishes to space telescopes, translate these vast distances into data we can plot. The raw numbers are often reduced to graphs and false color images, each pixel representing millions of light years. The reduction process inevitably filters the raw scale, shaping what we finally observe. Perspective also governs how we allocate resources for observation. A project aimed at a nearby star system requires a different budget and timeline than one targeting the cosmic microwave background, the afterglow of the universe's birth. The scale of the target dictates the scale of effort. One small fact remains. A photon that left the Sun at noon today will not reach the edge of the observable universe for over 13 billion years. That single particle carries a piece of our present into the deep past of the universe, a quiet reminder of how time and distance intertwine. The night sky above us still holds that photon, traveling through darkness, its path measured in minutes, years, and billions of years alike. The cold, dark stretches of a molecular cloud hide a restless pressure that refuses to stay still. Tiny grains of silicate and ice drift together, each collision adding a fraction of mass. Gravity, ever patient, begins to pull the loose material toward the densest points, like a slow-moving tide under a weightless sky. When a region reaches a critical density, the pull overwhelms the internal pressure and the gas starts to collapse. The collapse is not smooth. It fragments into filaments, then into knots that become the seeds of future stars. I find it hard to picture how a cloud the size of a small galaxy can contract to a sphere only a few hundred astronomical units across, yet observations keep confirming the pattern. The Orion Nebula offers a convenient laboratory for watching this process. At a distance of roughly 1350 light-years, its glowing pillars and dark lanes are resolved by telescopes that can separate structures the size of our solar system. In the trapezium cluster, several massive newborn stars already blaze, their ultraviolet light carving cavities in the surrounding gas. The nebula's brightness is a reminder that star birth is not a silent affair. Inside each collapsing knot, rotation becomes important. Conservation of angular momentum forces the material to flatten into a rotating disk. These protostellar disks are the first stage where a nascent star can gather the bulk of its mass. The central region heats up, and when temperatures climb above a few million Kelvin, hydrogen nuclei begin to fuse. The first sparks of fusion mark the moment a protostar steps onto the main sequence, shedding the surrounding envelope like a shell. The chemistry inside these clouds is richer than one might expect from a simple mixture of hydrogen and helium. Carbon, oxygen, nitrogen, and even more complex molecules form on dust-grained surfaces, later released into the gas phase. These elements are the building blocks of water, organic compounds, and eventually the chemistry that leads to life. It is a quiet reminder that the raw material for planets and biology is forged in the same places where stars ignite. As a newborn star settles into its steady burn, it does not simply sit idle. Stellar winds, streams of charged particles expelled at thousands of kilometers per second, push against the remaining gas. In some cases, the wind clears a bubble, halting further accretion onto nearby protostars. In other cases, the wind compresses adjacent filaments, potentially triggering another round of collapse. The feedback loop is a subtle balance between destruction and creation. Despite the wealth of data, we still lack a clear picture of how efficiently a cloud converts its mass into stars. Some regions turn a few percent of their gas into stars, while others seem to produce a much higher fraction. I don't really know why the efficiency varies so much. Magnetic fields, turbulence, and external pressure all play roles, but the exact weighting remains uncertain. We don't really know whether the observed variations are temporary phases or inherent properties of the clouds. Measurements of star-forming regions in different environments hint that the efficiency may depend on the cloud's initial conditions. Denser clouds tend to produce clusters of massive stars, whose winds and radiation quickly disperse the surrounding material, limiting further formation. More diffuse clouds may allow low-mass stars to form over longer periods, slowly draining the reservoir. The picture is still incomplete, and each new observation adds a small piece to a puzzle that refuses to settle. One way to test these ideas is to compare the Orion Nebula with more distant, massive star-forming complexes such as the Carina Nebula. While Orion offers a close-up view of low-mass star formation, Carina showcases how massive stars dominate the feedback. Both regions share the same basic ingredients: molecular gas, dust, gravity, but the outcomes differ markedly. The contrast underscores how sensitive the process is to initial mass distribution and external pressures. Even within a single cloud, the timeline of collapse can stretch over millions of years. The earliest phase, where a filament gathers enough material to become gravitationally unstable, may last a few 100,000 years. The subsequent protostellar stage, when the disk feeds the central object, occupies another few 100,000 years. Finally, the star reaches the main sequence and begins its long, steady life. The whole sequence is a slow, methodical transformation, not a sudden flash. Observations of infrared emission from dust reveal the temperature gradients within a collapsing core. The outer layers remain cold, around 10 Kelvin, while the inner regions heat up as material falls inward. These temperature differences affect the chemistry, allowing certain molecules to freeze onto grains in the cold outskirts while others remain in the gas phase near the core. The chemical signatures serve as a map of the physical conditions at each stage. Radio telescopes detect the faint emission of molecules such as Co, NH3, and H2O, tracing the motion of gas within the cloud. By measuring Doppler shifts, astronomers can infer how fast material is flowing toward the center, or being pushed outward by winds. The data often show a mixture of inward and outward motions, suggesting that collapse and feedback coexist in a tangled dance. The picture is far from simple, and each new measurement forces a revision of the models. In laboratory experiments, physicists attempt to recreate the conditions of a collapsing cloud using ultra-cold gases and magnetic fields. While the scales differ dramatically, the underlying physics, gravity like attraction, pressure support, angular momentum, can be simulated. These analogs provide a way to test how turbulence decays or how magnetic fields channel material, offering clues that are hard to extract from distant observations alone. The ultimate fate of the material that never becomes part of a star is also worth noting. Some of it remains as diffuse gas, later to be incorporated into future generations of clouds. Some is expelled into interstellar space by supernova explosions, enriching the galaxy with heavier elements. The cycle repeats, each iteration adding a thin layer of carbon or oxygen to the galactic reservoir. It is a slow, iterative process that builds the chemical richness we observe today. Even after a star ignites, its surrounding disk may persist for a few million years, providing the raw material for planets. The disk's composition reflects the earlier chemistry of the cloud, now altered by the heat and radiation of the newborn star. Observations of disks around young stars in Orion show gaps and rings that hint at planet formation already underway. The link between star birth and planet birth is therefore inseparable. One lingering question is why some clouds produce isolated stars while others generate dense clusters. The answer likely lies in the balance between gravity, turbulence, and external pressure from nearby supernova remnants. In regions where turbulence is low, gravity can dominate, leading to a rapid, clustered collapse. Where turbulence remains high, the gas fragments into many smaller cores, each forming a solitary star. The precise thresholds remain elusive. The Orion Nebula's bright core, illuminated by the trapezium stars, also casts shadows that outline the surrounding dust lanes. These shadows are not empty. They hide dense pockets where future stars may still be forming, hidden from optical view but glowing in infrared. The contrast between bright emission and dark silhouette provides a visual reminder that star formation is both visible and hidden, depending on the wavelength you choose. When I look at the faint glow of a distant nebula, I sometimes wonder how many of those tiny points of light will become suns like our own. The process that turns a cold, diffuse cloud into a blazing star is a cascade of physics, gravity, thermodynamics, chemistry, all working together over vast distances and timescales. It is a reminder that the universe builds its most complex structures from the simplest ingredients, one slow step at a time. A single filament in a molecular cloud, barely a few light years long, can host a chain of dense cores. In one such filament, a core of about 0.1 solar masses has just begun to show a faint infrared source, the first sign of a protostar. The core's temperature sits at 15 Kelvin, just above the surrounding gas. That tiny temperature rise is the only clue we have that fusion is about to start. When a cloud of cold hydrogen and helium finally gives way to gravity, the first steady beat begins. A newborn star settles onto the main sequence, its core a furnace where protons fuse into helium at a rate that balances the inward pull of its own weight. The energy that leaks out as visible light and a faint heat feels almost mundane compared with the forces at work. Yet, it is the only phase that lasts for most of a star's life. I find it hard to picture a single point of light holding such a delicate equilibrium for billions of years. As the hydrogen supply dwindles, the core contracts, heating up until helium can finally ignite. The outer layers respond by swelling, turning the star into a red giant that looms many times larger than its former self. The surface cools, giving the star a ruddy hue that betrays its inner turmoil. In this stage, the star begins to shed its skin, a slow wind that carries dust and heavier elements into the surrounding space. Occasionally, a thin, glowing shell of ionized gas detaches, forming a planetary nebula that drifts away like a fragile soap bubble. The next turn depends on the star's original mass. A star barely heavier than the Sun will simply shed its envelope, leaving behind a dense core about the size of Earth, a white dwarf that cools inexorably, a silent ember in the darkness. A heftier star, however, cannot stop the collapse. When the core exceeds roughly 8 solar masses, the pressure becomes too great for electron degeneracy to hold, and the star meets a violent end. A supernova erupts in an instant that feels almost absurdly brief. The core's implosion rebounds off nuclear forces, sending a shock wave racing outward at a sizable fraction of light speed. In that flash, elements heavier than iron are forged, and the star's outer layers are blasted into the interstellar medium. The explosion acts as a recycler, mixing fresh material into the galactic soup where new stars may someday arise. It doesn't quite make sense when you say it aloud, how a single event can both destroy and create at the same time. What remains after the blast depends again on mass. If the collapsed core lies between about 1.4 and 3 solar masses, neutrons pack together so tightly that the object becomes a neutron star. Imagine a sphere a few kilometers across that contains more mass than the Sun. A teaspoon of its material would outweigh a mountain. These remnants spin rapidly, sometimes dozens of times per second, and emit beams of radio waves that sweep across space like lighthouse flashes. Detecting those pulses requires precise timing, and each detection adds a point to the map of where massive stars have lived and died. When the core's mass tops roughly 3 solar masses, even neutron degeneracy cannot halt the collapse. Gravity wins, and the core contracts into a black hole, a region where the escape speed exceeds the speed of light. We cannot see the hole itself, but we infer its presence from the way nearby gas spirals inward, heating and emitting X-rays before disappearing beyond the horizon. The first detections came from binary systems where a normal star feeds material to an unseen companion, the X-ray glow acting as a subtle signpost. I don't really know how many of those lurk unseen, silent, in the outskirts of the Milky Way. Each type of remnant carries a record of the galaxy's past. White dwarfs trace the low-mass star population that has long ago left the main sequence. Their cooling ages, when measured precisely, give a lower bound on the time since the host region formed. Neutron stars, with their precise spin periods, mark the locations of recent massive star deaths, while black holes, though harder to spot, hint at the most energetic collapses. By cataloging these objects, astronomers can reconstruct the star formation history of a galaxy piece by piece, much like a paleontologist reads layers of sediment. The transformation from a shining main sequence star to a silent remnant is not a single line, but a series of thresholds, each set by the balance of pressure and gravity. The physics governing those thresholds is well tested in laboratories on Earth, high-pressure experiments, particle collisions. But the conditions inside a star are orders of magnitude beyond anything we can fully reproduce. We therefore lean on models that match observations, aware that the models are approximations. It feels a bit like trying to describe the taste of a distant fruit based only on its color. Even after the star's light has faded, its influence persists. The material ejected in planetary nebulae or supernovae enriches the interstellar medium with carbon, oxygen, iron, elements that later become part of planets, oceans, and perhaps life itself. In that sense, every star is a temporary conduit, moving matter from one form to another across eons. The remnants, scattered like a fossil record, remind us that the universe is constantly reshaping itself, even when we cannot see the motion. One quiet observation that often slips past the headlines. The nearest white dwarf, Sirius B, is barely brighter than the faintest stars we can see without aid, yet its surface temperature still exceeds 25.0 Kelvin. Its glow is a lingering echo of a star that once shone like the sun, now reduced to a cooling ember that will fade into invisibility over trillions of years. The night sky can hide objects that swallow light, yet we still manage to write notes about them. A black hole begins when a massive star can no longer support its own weight. Its core collapses and gravity overwhelms every other force. Sometimes the collapse is straightforward, A single star exhausts nuclear fuel, its iron core freezes, and the rest of the star rushes inward. Other times, two dead stars orbit each other for billions of years, lose energy, and finally merge. That merger creates a new horizon, larger than either predecessor, and releases a burst of gravitational waves. The surface we call an event horizon is not a solid shell. It is a sphere where the escape velocity equals the speed of light. Cross that line and nothing, not even photons, can climb back out. We cannot see inside, but we can infer its size from the mass we measure. Mass tells us the radius of the horizon, roughly 3 kilometers per solar mass. A 10 solar mass black hole therefore hides a sphere the size of a small city. It feels absurd to think of that amount of matter compressed into such a tiny volume. I find it hard to picture the pressure at the center. General relativity predicts a singularity at the core, a point where curvature becomes infinite. Mathematically, the equations break down, offering no description of physics there. That failure tells us the theory is incomplete, not that the universe contains actual infinities. We don't really know what replaces the singularity in a full quantum description. Stephen Hawking suggested that black holes are not completely black. Quantum fluctuations near the horizon can produce particle pairs, one falling in while the other escapes. The escaping particle carries away a tiny amount of energy, making the whole lose mass over eons. That process is called Hawking radiation, and it raises a paradox: information that fell and seems to disappear. If information truly vanishes, the basic rule of quantum mechanics, unitarity, fails. Physicists have argued for decades about whether the radiation somehow encodes the missing data. No experiment can yet test the effect, because the temperature of Hawking radiation for stellar black holes is far below the cosmic microwave background. It doesn't quite make sense when you say it aloud. A hot object cooler than the surrounding space. The first direct evidence of black holes came not from light, but from ripples in spacetime. In 2015, detectors in the United States caught a fleeting chirp, a pattern matching the merger of two 10 solar mass holes. The signal rose in frequency, peaked, then faded as the new black hole settled. That observation confirmed that gravity can carry energy across the universe in wave form. Since then, dozens of mergers have been cataloged, each adding a data point to the mass distribution map. Some events involved black holes 30 times the mass of the Sun, hinting at a different formation channel, perhaps the collapse of a massive, low-metallicity star. Other events showed spins aligned with the orbital plane, suggesting a common origin in a binary system. Each detection refines our models, yet the underlying physics of the final plunge remains a blur. A different kind of observation arrived in 2019, when a network of radio telescopes painted a silhouette against glowing gas. The image showed a dark disk about 40 micro-arcseconds across, surrounded by a bright ring. That dark region matches the predicted shadow of the supermassive black hole at the center of Galaxy M87. The ring's brightness varies, likely because of hot plasma swirling at near-light speed. The shadow's size agrees with the mass measured from the motions of nearby stars, confirming that the object's gravity bends light exactly as Einstein's equations predict, at least outside the horizon. Inside that ring, the photon paths are twisted into loops, some completing multiple orbits before escaping. The pattern of brightness tells us about the magnetic field geometry, but it does not reveal the interior. Even with the shadow, we still lack a picture of what lies at the center. Quantum gravity proposals, string theory, loop quantum gravity, or something else, offer speculative pictures such as a fuzzball or a bounce. These ideas attempt to replace the singularity with a finite structure that preserves information. We have no empirical way to decide yet. What we can measure are the effects on surrounding matter. Accretion disks heat up, emit X-rays, and sometimes launch narrow jets that pierce interstellar space. The jet's direction stays fixed for millions of years, suggesting a stable spin axis. If the spin is extreme, the horizon's shape becomes slightly oblate, a subtle deviation we may detect with future interferometers. The community also watches for potential echoes in gravitational wave signals, tiny repetitions that could indicate a reflective surface just outside the horizon. So far the data are inconclusive, but the search continues, driven by the same curiosity that led to the first detection. Each null result narrows the space of viable theories. In the lab, we simulate aspects of horizon physics with analog systems, water waves, Bose-Einstein condensates, or optical fibers. These platforms can mimic Hawking like emission, offering a tabletop glimpse of a process that would otherwise require a star-sized black hole. They do not prove the astrophysical mechanism, but they keep the discussion grounded in experiment. The picture that emerges is one of extreme simplicity and bewildering complexity. A black hole can be described by just mass, spin, and electric charge, yet it forces us to confront the limits of our most successful theories. It is a reminder that the universe can hide its most interesting secrets behind an invisible wall. Tonight, as the telescope points toward the galaxy's heart, a faint glow outlines a dark circle. The ring's edge flickers, a whisper of photons that have skirted the point of no return. That flicker, caught by a network of dishes, is the only clue we have of the abyss inside. The night sky, when stripped of its familiar constellations, reveals a pattern of islands, vast collections of stars bound together by gravity. Those islands fall into three broad families: graceful spirals with winding arms, roundish ellipticals that lack structure, and irregulars that refuse any tidy classification. I find it hard to picture how a single galaxy can contain 100 billion suns and still appear as a faint smudge through a modest telescope. Spiral galaxies, like the one we call home, spin because their stars inherit angular momentum from the cloud that birthed them. Their disks are thin, a few thousand light-years thick, yet they stretch outward for over 100,000 light-years. In the center, a bulge of older stars sits like a dense core, often hosting a supermassive black hole that quietly shapes the surrounding motion. Elliptical galaxies are the opposite extreme. They lack a disk, presenting instead a smooth, three-dimensional shape that can range from nearly spherical to highly elongated. Their stars move on random orbits, giving the galaxy a frosted appearance. Many of the most massive ellipticals sit at the heart of clusters, where repeated mergers have erased any trace of spiral arms. Irregular galaxies defy the neat categories. Their shapes are warped by tidal forces, recent collisions, or bursts of star formation. Some are small, dwarf systems that barely hold together. Others are massive enough to rival spirals but have been scrambled by a close encounter. Their chaotic look reminds us that the universe is not a tidy laboratory, but a place where gravity constantly reshapes matter. All these families sit inside invisible envelopes of dark matter. The halos extend far beyond the visible edge, containing most of a galaxy's mass. We cannot see the halos directly, yet their gravitational pull is evident in the rotation curves of spirals and the motions of satellite galaxies. I don't really know what dark matter is, but its presence is unavoidable in any attempt to map the large-scale structure. When we look beyond a single galaxy, we see that galaxies are not scattered randomly. They gather in groups, then clusters, and finally in superclusters that stretch across hundreds of millions of light-years. These aggregations trace a network of filaments, thin, elongated bridges of matter, interspersed with vast emptiness we call voids. The pattern resembles a web, though the term cosmic web feels overused, I prefer the large-scale web to keep the description grounded. The filaments are composed of both galaxies and the dark matter that binds them. Gravity pulls matter into these strands, while the expansion of space stretches the whole pattern. In the densest knots, clusters merge, forming some of the most massive structures known. In the emptiest regions, the density drops to a fraction of the average, leaving a near vacuum that stretches for tens of millions of light years. Observations of distant supernovae revealed that the expansion of the universe is not slowing down as once thought, but accelerating. The driver of this acceleration is called dark energy, an unknown component that fills space uniformly. Its effect is subtle on small scales, but dominates the dynamics of the universe as a whole. I find it hard to picture a force that pushes everything apart without pulling on anything directly. If dark energy continues to dominate, the future of the universe may head toward a state called heat death. In that scenario, galaxies drift farther apart until they can no longer exchange photons or particles. Stars burn out, black holes evaporate, and the remaining matter reaches a uniform low temperature. The night sky would become a dark, featureless expanse. Another speculative outcome is the Big Rip. If the repulsive effect of dark energy grows stronger over time, it could eventually overcome all binding forces, first pulling apart galaxy clusters, then individual galaxies, and finally tearing apart stars and atoms. The mathematics allow for such a possibility, but we lack direct evidence that the dark energy density is changing in that way. A third class of ideas returns to cycles. Some models propose that the current expansion will reverse after an immense time, leading to a contraction that culminates in a bounce, perhaps spawning a new expansion phase. Others suggest that quantum fluctuations could generate new regions of space, each with its own physical parameters in a kind of multiverse. These concepts are intriguing, yet they sit at the edge of what we can test. Our own galaxy sits in a modest filament that connects the local group to the larger Virgo supercluster. The Milky Way and Andromeda will merge in a few billion years, forming a larger elliptical remnant. That future merger is a tiny episode in the grander flow of matter along the filament, which itself will be stretched by the accelerating expansion. When we consider the scale of these structures, the numbers become almost incomprehensible. A typical filament may be a few megaparsecs across but stretch for 100 megaparsecs in length. 1 megaparsec equals 3 million light-years, so the filament's length can be on the order of 300 million light-years, far larger than any galaxy. The voids between filaments can be twice as wide, leaving empty pockets that swallow any light that tries to cross. Even the notion of distance changes over cosmic time. As space expands, the light from a distant galaxy is stretched, shifting its spectrum toward longer wavelengths. This redshift is a direct measure of how much the universe has grown since the light left its source. In the far future, the redshift will become so extreme that photons from most galaxies will be stretched beyond detection. The large-scale web is not static. It evolves as matter flows along filaments toward nodes, where clusters grow. Simulations that start from the early universe's tiny density fluctuations reproduce the web's appearance remarkably well, suggesting that gravity alone can sculpt the observed pattern. Yet we still lack a complete picture of how baryonic matter, gas, dust, stars, interacts with the dark scaffolding to produce the luminous structures we see. Our place in this ever-changing architecture is modest. The solar system occupies a quiet corner of a spiral arm, far from the bustling cores of clusters. The night sky we admire is a fleeting snapshot, captured before the acceleration has erased most distant galaxies from view. In a few tens of billions of years, the only galaxies we could still see would be those bound to our local group, all others receding beyond the horizon. The future also holds a quiet shift in the cosmic background. As the universe expands, the relic radiation cools, dropping from its current temperature of about 3 Kelvin toward ever lower values. Eventually, the background will be colder than any remaining heat source, making it virtually undetectable. The universe will become a cold, dark place, with only the faint whisper of quantum fluctuations remaining. I sometimes wonder whether our current instruments could ever capture the moment when the last observable galaxy slips beyond reach. The idea feels both absurd and intimate, as if the universe is quietly withdrawing its light, leaving us with a dimming glow that we can still measure. It doesn't quite make sense when you say it aloud. The universe, once teeming with brilliant islands, becoming a silent, cold field. One small detail persists, however. Even in the most empty voids, a few stray hydrogen atoms linger, their occasional spin-flip transition emitting a photon at a characteristic wavelength of 21 centimeters. Those rare emissions are the faintest whispers we can still detect, a reminder that absolute emptiness never truly exists.